Hey y'all, Rusty Rob here, welcome to another video. Today I'm really excited to show you a cutting edge cheating detection algorithm. So we can process over a gigabyte of test data in less than half a second. So it's pretty optimized using a thread pool, cache padding, pool of buffers, ndarrays as well. So we're using SIMD to do multiple operations with one instruction on the CPU. So similar to Python's numpy, Rust has a ndarray. So that was pretty interesting to use that. And for background, this problem actually came from a Google contest a few years ago. And at the time I wrote a solution in Go during the contest and came up with a pretty creative solution that I always wanted to show on the channel. And just for reference, the cutting edge solution at the time was 90% accurate, and this is close to 100% accurate. So it's a pretty cool trick to make sure we can see who the cheater is very accurately. And the implementation is actually pretty straightforward as well. So let's have a look at the problem, and then I'll go through the code. So here's the problem statement. I'll link this in the description. But basically, you're given a binary matrix of ones and zeros. So the columns is each question and the rows is each player in the game show. And we'd get a 1 or 0 depending on if they got the question right or not. And we're also told that the players have an even distribution of skills. The questions have an even distribution of difficulty. And so based on that, determines the probability of them getting the right answer. And if you want to know more about that, it's just using the sigmoid function of the difference between the skill and the difficulty. Now, how can we analyze this data to determine the cheater? It's hard to know which data we can trust, like which values can we actually trust, right? Well, one thing we can get pretty accurately is the difficulty of each question. We can just look at a column and see on average how many people got it correct. And it's not going to be affected too much by the cheater. Now let's look at a player, right? And let's say the questions are ordered from easiest to hardest. So then you've got more ticks to the left and more crosses to the right. And we don't know if this player cheated or not, right? But if we pull down the ones they got wrong and the ones they got right, let's look at those separately. So I think that's one of the key insights, is that if it's an X, we know that the player didn't cheat, because otherwise they would have got it right. So I probably should have mentioned that the player flips a coin. If they get heads, they cheat and they get it right. Otherwise they just give it their best shot. So we know that these values are accurate. And so we can look at the average difficulty. So if we assume these are positioned on an X coordinate, X axis based on difficulty, the average difficulty is about here. And then if we look at the ones, if we look at the ones they got right, the average difficulty is about here. Now, we don't know if this is accurate though, because we don't know if they cheated or not, right? So what happens if they didn't cheat, right? Because this is after the fact, after they've cheated. Well, if they didn't cheat, which of these would they have got wrong? Well, I'd argue that it's more likely that they would have got the harder questions wrong, right? Whereas cheating on an easy question's unlikely to have any effect, because you're probably going to get that right anyway. So what that means is this average would move to the left. So it should have actually been over here, because this should probably be more likely to be an X, right? So these values are the three values that are the key to solving this problem. And the last trick is, well, how do we find out this value? Well, because we know this value is accurate, we also know that because this curve is smooth and monotonically increasing, if we rank everyone based on this value, then it's the same as ranking them based on their skill. So we can write that if x is less than y, then f of x is less than f of y. Try to make that a bit bigger, but yeah. So we can basically do a sort. So without actually knowing the player's skill levels, we can rank them based on skill. And then once we've done that, we can look at the nearest neighbor. So we can look at their neighbor's value for this. And we know that's accurate because their neighbors didn't cheat. There's only one cheater. And then we can look at the player's actual value of this. And so then we can compare these two values, and we can just look at the maximum. We'll call that like an enhancement. So that's how much they enhanced from cheating. And we can just look at the maximum enhancement across all of the players. So it's actually a pretty straightforward algorithm, but I don't think anyone else came up with it. So yeah, I was pretty happy with that. So this is just some code that generates some test data. So let's go through the code. And I've put a bit of a description here so you can check it on GitHub if you want. I'll link that in the description. So this is pretty cool by Crossbeam. It just pads things to a cache line. So it means that different threads can cache data efficiently. I didn't actually check to see if it made much difference, but it's pretty cool using a thredpool, and we're using a sync channel, which means we can have a pool of buffers and a pool of ndarrays, and we can just reuse those. So so we have a reader that's just reading the file at max speed into buffers. I'll get to that in a second. We have some constants, just n is the number of people, m is the number of questions. We have a person. This is the average wrong that I was talking about. So this value here. And this is the average right, which is this value here. And then this is the predicted average right, which is this value here. And then this is just what calculates the enhancement. So we just read the file, and we read an entire matrix at a time, and we don't even need to check for new line characters. So we set up a pool of matrices and a pool of buffers. So for that, I'm just using a sync channel, which means I just loop through this vector of ndarrays, and I send the matrix to the matrix channel. And I also send some buffers to the buffer channel. So we go through each, we set up a pool with, I think, 20 workers. We read exact. So the buffer is the exact right size for a matrix. So this should be super fast. So this is what is costing us work in the main thread. Everything else is pretty much instant. Like, we should always have a buffer available. We shouldn't run out of buffers. So that's instant. And then all of these should be instant, right? We should always have a matrix available. And then in a separate thread, we're just moving all of this stuff. And so it's a separate thread that's taking that buffer, turning it into a matrix, and then doing the operations. So straight away, we're reading the next buffer. Now, thredpool has this execute method, which will wait for one of our threads to come available. We have enough threads that it should pretty much always be pulling straight away. We have lots of threads in just one reader, so this should be running a lot faster than this, and this is running at max speed. So we shouldn't really be able to have any performance gains. Now here we're just going through the matrix, we're zipping the matrix with the buffer, and here I'm just saturating sub. I'm just converting the 1 or the 0 to an F32, but it could also be a new line character, and that's why if it's a new line character, I just treat it as a 0 and it doesn't affect the results. So the last column in the matrix is just zeros. But yeah, it just means we don't have to have any branching, which I guess would speed it up. So we're done with that buffer. We've converted it into this matrix that we got from the matrix pool. So we just send that buffer back. Now we get the sum of each column and then divide it by the number of people. So that's giving us the difficulty of each problem. And then we want the average, right? Which was this one. So what we're just going to do is we can just do a dot product, and then we need to make sure we normalize it by how many they actually got right. So zeros don't affect this. And so that's for each player, that's just giving us this value. And then we can do pretty much the exact same for the ones they got wrong. But before we do that, we do this little in place trick where we change every value from, well, every value in the matrix we change. If it's a 1, we subtract it from 1 and it'll change to a 0, and a 0 will change to a 1. And we are also inverting the difficulty. Yeah, I'm not sure why I inverted the difficulty actually. Maybe I could have left that. Anyway, so send the matrix back because we've got the values we need. And then just go through the people and just assign those results to the person. And just record the ID so that we can output the results later on. And then here we're just sorting the people by the average wrong. So that's basically the same as sorting them by skill. Then we're looking at the nearest neighbors. So we're going 2 to the left and 2 to the right. And we're just taking an average of that. So now we get this prediction value. So now we can use this cheating enhancement function that we made earlier. And just take max by, that's just handy. We can just use that function to grab the maximum value. So we've got the cheater there, and then we just return the test case and the cheater's ID. So I've got this results channel, so I'm just constantly sending results to that. And when I first ran this, I actually had a bug because I didn't drop the sender of the results channel. And so when I was here, I'm just reading results from that channel. And after all of these threads had finished executing, basically this goes out of scope as soon as the execution is finished. However, this was still waiting to receive because this hadn't been dropped yet. So I just had to drop the last value of that. And then once that drops, like internally, a channel has something like a reference counter, which it basically counts how many copies of the sender there are. And once that goes to 0, then it basically sends a terminating error. So then this would be an error, and so then this would end. And then here, the results could come out of order, so I just sort them again and print them out. One other bug I had was I forgot to divide by the row sum. And it's important to do that because if you can imagine one player that just got like one extra question right or one extra question wrong, that would just mess up the total. So we need to make sure we normalize by dividing by the number of problems we're considering. Yeah, so if we run that, it runs really quickly. You can run that again. Running a bit slower now, maybe because I've got the video running, but still pretty quick. And we can look at that out file. And I'm also doing a diff here to make sure it's correct, so there's no diffs. So yeah, I thought that was a really interesting problem, and it was pretty fun implementing it with Rust using these sync channels, which, you know, take a buffer size and things like that. So yeah, thanks a lot for watching, and hope you give it a try yourself. And yeah.